In meteorology, a cloud is an aerosol consisting of a small visible mass of liquid water droplets, frozen crystals, or other particles suspended in the atmosphere of a dry planetary body or similar space. Water or many other chemicals can form droplets and crystals. On Earth, clouds form from saturation of air when it cools to its dew point, or when enough moisture is added from a nearby source to raise the dew point above the ambient temperature. They are found in the Earth's atmosphere, which includes the troposphere, stratosphere, and mesosphere. The study of clouds is the science of clouds, conducted within the cloud physics branch of meteorology. There are two methods of naming clouds in their respective layers of the atmosphere. The genus species in the troposphere, the layer of the atmosphere closest to the Earth's surface, have Latin names because of the popularity of Luke Howard's nomenclature, which was formally proposed in 1802. It became the basis of a modern international system that divides clouds into 5 physical forms that can be further subdivided or classified into altitude levels to derive 10 basic genera. The main representative cloud types for each of these are stratus, cumulus, stratocumulus, cumulonimbus, and cirrus. Low-level or low-level clouds do not have any altitude prefix. In the stratosphere and mesosphere, clouds have common names for their main types. They may have the appearance of stratiform sheets or networks, ring-like wrinkles, or stratiform bands or ripples. They are not commonly seen, mainly in the polar regions of Earth. Clouds have been observed in the atmospheres of planets and moons in the solar system and beyond. However, due to their different temperature characteristics, they often include other substances such as methane, ammonia, and sulfuric acid, as well as water. Tropospheric clouds can have a direct impact on climate change on Earth. They can reflect incoming rays from the sun, which can contribute to a cooling effect. Where and when these clouds occur, or trapping longer wave radiation reflected back from the Earth's surface, can cause a warming effect. The height, form, and thickness of clouds are major factors influencing the local heating or cooling of the Earth and its atmosphere. Clouds forming in the upper troposphere are too rare and too thin to have any influence on climate change. Clouds are a major source of uncertainty in climate sensitivity. Water vapor condenses to form tiny water droplets or ice crystals, which, together with billions of other tiny water droplets or ice crystals, form the clouds that humans can see. Clouds reflect all visible wavelengths of light equally, and are therefore white, but we can also see gray or blue clouds if they are too thick or dense for light to pass through. Clouds on other planets typically contain other types of substances besides water, depending on the conditions of their atmospheres. First, water vapor will rise into the air. With this process, when the weather temperature increases, the amount of water vapor in lakes, rivers, and seas will evaporate into the atmosphere. Roll clouds, noctilucent clouds, mother-of-pearl clouds, funnel clouds, virga clouds, hole clouds, asperitas clouds, maternity clouds. Cloud density is a concept used to indicate the distribution of clouds in the sky, thick or thin, many or few. This concept depends on the evaporation and condensation of water particles in the atmosphere. At night, the more clouds, the harder it is for the moon to appear. The origin of the term cloud can be found in the Old English words clud or clod, meaning a hill or a mass of rock. Around the early 13th century, the word was used as a metaphor for rain clouds, because of the similarity in shape between a rock mass and a cumulus cloud. Over time, the metaphorical use of the word replaced the Old English welcan, which was a term for clouds in general. Studies of ancient clouds are not done in isolation, but are observed in conjunction with other weather factors and even other natural sciences. Around 340 BC, the Greek philosopher Aristotle wrote Meteorology, a work that represents the sum total of the era's knowledge of natural sciences, including weather and climate. Rainfall and the clouds from which it falls were first called meteors, from the Greek word meteoros, meaning in the high sky. From this came the modern term metecology, the study of clouds and weather. Meteorology is based on intuition and simple observation, but not on today's scientific method. However, this is the first known work that attempted to treat a wide range of meteorological topics systematically, especially the hydrological cycle. Terrestrial clouds can be found throughout most of the atmosphere, including the troposphere, stratosphere, and mesosphere. In these layers of the atmosphere, air can become saturated by being cooled to its dew point or by the addition of moisture from a nearby source. In the second case, saturation occurs when the dew point is raised to equal the ambient air temperature. Clouds form in areas of cooled, moist air, generally by rising. It can occur. Clouds are relatively heavy. The water in typical clouds can weigh millions of tons, although each cubic meter of cloud contains only about 5 grams of water. Water droplets in clouds are about 1,000 times heavier than water vapor, so they are heavier than air. The reason they don't fall, but are held in the atmosphere, is because the liquid water droplets are surrounded by warm air. The air is warmed by the heat energy released when water condenses from water vapor. Because the water droplets are so small, they stick to the warm air. As clouds form, the warm air expands rather than decreases in volume after water vapor condenses, causing the clouds to rise, and then the density of the cloud decreases to the average density of the air, and the cloud drifts through the air. The actual shape of the cloud formed depends on the strength of the lifting force, and on the stability of the air. Under conditions where convective instability dominates, vertical cloud formations are formed. Stable air produces mainly horizontally homogeneous clouds. Uplift along fronts produces different cloud forms, depending on the composition of these fronts on a or cut-off form of warm or cold fronts. Uplift also produces different cloud forms, depending on the stability of the air, although cap clouds and wave clouds are typical of uplift clouds. Convective classification is based on a hierarchy of types with physical forms and elevations at the top. They are cross-classified into a total of 10 genera, most of which can be divided into species, and further divided into genera at the bottom of the hierarchy. Tropospheric clouds are assumed to have 5 physical forms based on their structure and formation. These forms are commonly used for satellite analysis purposes. They are given below in order of increasing instability or convective activity. Non-tropical clouds occur in stable air mass conditions and are generally flat, sheet-like structures that can form at any altitude in the troposphere. The stratigraphic group is divided according to altitude range into stratostratus high level, Mesopotamia middle level, stratostratus low level, and nimbostratus multi-level cloud branches. Fog is generally considered to be a surface cloud layer. Fog can form at surface level in clear air, or it can be the result of a very low stratigraphic cloud that sinks to the ground or sea level. In contrast, low stratiform clouds result when convective fog is lifted above the surface in light wind conditions. Tropospheric ring clouds are of the cirrus variety and have the appearance of loose filaments or threads. They form at high tropopause altitudes in the atmosphere, which is largely stable with little or no convective activity, although denser patches can sometimes show accumulation due to limited upper-level convection where the air is partially unstable. Similar clouds such as cirrus, cirrostratus, and cirrostratus can be found above the troposphere, but are classified separately using common names. Clouds of this structure have both cumulus and stratiform characteristics in the form of rolls, ripples, or particles. In general, they form by confined convection in a quasi-stable air mass covered by an inversion layer. In the absence of an inversion layer or higher in the troposphere, the instability of the rising air mass can cause cloud layers to develop tower-like tops consisting of embedded cumulus masses. The stratigraphic structure group is divided into cirrocumulus high level, stratospheric prefix, altocumulus middle level, stratospheric prefix, and stratocumulus low level. Cumulus clouds often occur as discrete clusters or plumes. They are the product of local lift, but are generally free convection, where there is no inversion layer in the troposphere to restrict vertical growth. In general, small cumulonimbus clouds tend to show relatively weak instability. Larger cumulonimbus cloud forms are an indication of greater atmospheric instability and convective activity. Depending on their vertical extent, cumulus clouds can be low-level or multi-level with moderate vertical extent. The largest free convective clouds include cumulonimbus clouds, which have towering vertical extents. They occur in highly unstable air and often have faint outlines in the upper part of the clouds that sometimes include the tops of anvils. These clouds are the product of very strong convection that can penetrate the lower stratosphere. When rainfall reaches the ground without completely evaporating, it is called precipitation or precipitation. This usually occurs in opaque upper layers, can produce widespread but usually light rainfall, and with thicker clouds showing considerable vertical development. Of these, upward developing mesocumulus clouds produce only light showers, while downward developing nimbostratus clouds down have the potential to produce heavier, more widespread rainfall. Towering vertical clouds have the greatest potential to produce intense rainfall events, but these clouds tend to be localized unless organized along fast-moving cold fronts. Moderate to heavy showers may fall from cumulus clouds. Cumulonimbus clouds, the largest of all clouds, are capable of producing very heavy showers. Low-level clouds usually produce only light rainfall, but this does happen in the form of characteristic precipitation, precipitatio, due to the fact that this type of cloud is located too close to the ground to allow the formation of virga. Clouds initially form in clear air, or become clouds when fog rises above the surface. The type of cloud that forms is determined primarily by characteristics of the air mass, such as stability and humidity. If these characteristics change over time, the branch tends to change accordingly. When this happens, the original branch is called the parent cloud. If the parent cloud retains most of its original shape after the new type appears, it is called a genitis-born cloud. An example of this is the cumulonimbus, a stratocumulus cloud formed by the division of partial dispersion of the cumulus type when there is a loss of convective lift. If the parent cloud undergoes a complete change in type, it is considered a mummatus cloud. Although the local distribution of clouds can be significantly influenced by topography, the global prevalence of cloud cover in the troposphere tends to vary more with latitude. It is most common in and along low-pressure zones of surface tropospheric convergence that surround the Earth near the equator and near 50 degrees latitude in the northern and southern hemispheres of the Earth. The adiabatic cooling processes that lead to the creation of clouds by means of lifting agents all involve convergence, a process involving horizontal airflow and the accumulation of air at a given location, as well as the speed at which this occurs. Near the equator, increased cloudiness is due to the presence of low-pressure intertropical convergence zones, where very warm and unstable air forms mostly cumulonimbus and cumulonimbus clouds. Almost any type of cloud can form along mid-latitude convergence zones, depending on the stability and moisture content of the air. These extratropical convergence zones are occupied by the polar front, where air masses, polar regions meet and collide with tropical or subtropical regions. This results in the formation of extratropical cyclones consisting of cloud systems that can be stable or unstable to varying degrees, depending on the stability properties of the different conflicting air masses. The luminosity or brightness of a cloud is determined by the way light is reflected, scattered, and transmitted by the cloud particles. Its brightness can also be affected by the presence of clouds or photoperiodic phenomena such as halos and rainbows. In the troposphere, deep, dense clouds exhibit high reflectivity 70 to 95% throughout the visible spectrum. The tiny water droplets are packed densely, and sunlight cannot penetrate far into the cloud before reflecting back out, giving the cloud its characteristic white appearance, especially when viewed from above. Cloud droplets tend to disperse light efficiently, so the intensity of solar radiation decreases with depth of the gas. Therefore, the cloud base can vary from very light to dark gray, depending on the thickness of the cloud and how much light is being reflected or transmitted back to the observer. Thin high tropospheric clouds reflect less light due to the relatively low concentration of constituent ice crystals or supercooled water droplets, resulting in a whitish appearance. However, a dense cloud of ice crystals appears brilliant white with a distinct grayish shade because of its greater reflectivity. As a tropospheric cloud matures, dense water droplets can combine to form larger droplets. If the droplets become too large and heavy to be held in the circulating air, they fall from the cloud as rain. By this process of accumulation, the space between the droplets becomes larger and larger, allowing light to penetrate deeper into the cloud. If the cloud is large enough and the droplets within are spaced far enough apart, a percentage of the light that enters a cloud is not reflected but absorbed, making the cloud appear darker. A simple example of this is that a person can see further in heavy rain than in dense fog. The reflection or absorption process is what causes the color range of clouds from white to black. The color of the cloud can be seen at any altitude, with the cloud color often similar to the incident light. During the day, when the sun is relatively high in the sky, tropospheric clouds often appear bright white above with varying shades of gray below. Thin clouds may appear white or appear to have taken on the color of their environment or background. Red, orange and pink clouds appear almost exclusively at sunrise or sunset, and are the result of the scattering of sunlight by the atmosphere. When the sun is just below the horizon, low-level clouds are gray, mid-level clouds are pink, and high-level clouds are white or off-white. Clouds at night appear black or dark gray in a moonless sky, or white when illuminated by the moon. They can also reflect the color of large fires, city lights, or auroras that may be present. A cumulonimbus cloud that appears green or bluish in color is a sign that it contains extremely high amounts of water. Hail or rain scatters light in a way that makes the cloud appear blue. Green occurs mainly late in the day when the sun is relatively low in the sky, and the reddish incident sunlight appears green when illuminating a very high bluish cloud. Supercell storms typically have this characteristic, but any storm can appear this way. This color does not directly indicate that it is a severe thunderstorm. It just confirms its potential. Since green or blue indicates abundant water, strong currents to support it, high winds from the storm pouring down, and wet hail, all factors that improve the chances of it becoming severe. All of this can be inferred from this. Additionally, the stronger the ocean current, the more likely the storm is to experience tornadoes and produce large hail and high winds. Yellowish clouds can be seen in the troposphere during the late spring to early fall months during wildfire season. The yellow color is due to the presence of pollutants in the smoke. Yellow clouds are due to the presence of nitrogen dioxide and are sometimes seen in urban areas with high levels of air pollution. Tropospheric clouds have many effects on the Earth's climate and troposphere. First and foremost, they are the source of precipitation, thus greatly influencing its distribution and amount. Because of their distinct buoyancy relative to the surrounding cloudless air, clouds can be associated with vertical movements of air that can be convective, frontal, or cyclonic. Upward motion occurs if the clouds are less dense, because the condensation of water vapor releases heat, warming the air, and thus reducing its density. This can lead to downward motion because the uplift of the air results in cooling, which increases its density. All these effects depend delicately on the vertical temperature and moisture structure of the atmosphere, and result in large redistributions of heat that affect the Earth's climate. Assessing the impact of current clouds on current climate is difficult. Predicting future changes in cloud patterns and properties, a warmer climate, and the resulting cloud impacts on future climate is even more difficult. In warmer climates, more water will enter the atmosphere by evaporation at the surface. Since clouds are formed from water vapor, cloudiness will increase. But in a warmer climate, higher temperatures would tend to evaporate clouds. Both of these claims are considered correct, and both phenomena, known as cloud feedbacks, are found in climate model calculations. More broadly, if clouds, especially low clouds, increase in a warmer climate, the cooling effect leads to negative feedbacks in the climate response to increased greenhouse gases. But if low clouds decrease, or if high clouds increase, then the feedback is positive. The different amounts of these feedbacks are the main reason for the differences in the climate sensitivity of current global climate models. As a result, many studies have focused on the response of low and vertical clouds to a changing climate. However, leading global models produce quite different results, with some showing an increase in low clouds and others showing a decrease. For these reasons, the role of tropospheric clouds in regulating weather and climate remains a leading source of uncertainty in projections of global warming. Recently, it has been recognized that the phenomenon of global dimming is caused by changes in the light reflectance of clouds due to the increased presence of suspended particles and other particles in the atmosphere. Subtropical stratospheric clouds (PSES) form in the lowest part of the stratosphere during winter, at the altitude, and during the season that produces the coldest temperatures, and therefore the best opportunity to trigger condensation due to adiabatic cooling. Moisture is scarce in the stratosphere, so nacreous and non-nacreous clouds at this altitude range are limited to the polar regions in winter, where the air is coldest. Supercooled nitric acid and PCSC water, sometimes referred to as Type 1, often have a stratified appearance resembling cirrus clouds or fog, but because they do not solidify into crystals, they do not display the chalky color of nacreous types. This type of PCSC has been identified as a cause of stratospheric ozone depletion. Frozen nacre is typically very thin, pearly in color, and appears as annular or lenticular layered undulating pattern. It is sometimes referred to as Type 2. Stratospheric clouds form at extreme altitudes of about 80 to 85 kilometers. They are named after the Latin noctilucent clouds because of their excellent illumination after sunset and before sunrise. They are usually bluish or silvery white in color and can resemble brightly lit cirrus. Noctilucent clouds can sometimes be more red or orange in color. They are not common or widespread enough to have a significant impact on climate. However, the increasing frequency of noctilucent clouds since the 19th century may be a result of climate change. Clouds form when water vapor rises, cools, and condenses in the air as tiny droplets. These tiny droplets are relatively dense, and light cannot penetrate very far into the cloud before it is reflected back out, giving clouds their characteristic white color. As clouds thicken, droplets can join together to form larger drops, which then, when large enough, fall to the ground as rain. During accumulation, the space between the droplets becomes larger, allowing light to penetrate deeper into the cloud. If the cloud is large enough, and the water droplets are far enough apart, then very little of the light that enters the cloud is likely to be reflected back out before it is absorbed. This reflection or absorption process is what leads to the wide range of cloud colors, from white to gray and black. Other colors occur naturally in clouds. The bluish-gray color is the result of light scattering in clouds. In the spectrum, blue and green have relatively short wavelengths, while red and yellow have long wavelengths. Short wavelengths are easily scattered by water droplets, and long wavelengths are easily absorbed. The bluish-gray color is evidence of scattering produced by rain-sized water droplets in the clouds. Foul colors are seen before severe weather events. The greenish color of clouds is produced when light is scattered by ice. Cumulonimbus clouds with a greenish color are a sign of heavy rain, hail, strong winds, and possibly tornadoes. Yellow clouds are rarer, but can occur during the late spring to early fall months due to wildfires. The yellow color is probably caused by the presence of smoke. Red, orange, and pink clouds occur mainly at dawn or dusk, and they are the result of the scattering of light by the atmosphere. Clouds themselves do not have these colors. They only reflect the long unscattered rays of light, which are the dominant wavelengths in that time period. The afternoon before a tornado in Edmonton, Alberta in 1987, Edmontonians observed red clouds on the sunward side and dark black clouds on their dark side. In this case, the saying "red sky at night, sailor's delight" is completely wrong. Cloud cover has been seen on most other planets in the solar system. Venus' thick clouds are composed of sulfur dioxide due to volcanic activity, and appear to be almost entirely stratiform. They are arranged in 3 main layers at altitudes of 45 to 65 kilometers that obscure the planet's surface and may create virga. No type of embedded cumulus has been identified, but broken stratigraphic wave formations are sometimes seen in the top layer, exposing more continuous layer clouds below. On Mars, noctilucent rocks, cirrus, stalactites, and strata composed of water ice have been detected, mostly near the poles. Water ice fog has also been detected on Mars. Both Jupiter and Saturn have an outer ring-shaped cloud layer composed of ammonia, an intermediate layer of stratocumulus clouds made up of ammonium hydrosulfide, and an inner layer of cumulus clouds. Embedded cumuli are known to exist near the Great Red Spot on Jupiter. Similar types can be found on Uranus and Neptune, but they are all made of methane. Saturn's moon Titan has cirrus clouds thought to be composed primarily of methane. The Cassini-Huygens mission to Saturn discovered evidence of polar stratospheric clouds and the methane cycle on Titan, including lakes near the poles and silt channels on the moon's surface.